The shifting property of the Laplace transforms is one of the most important properties of the Laplace transforms. So the shifting property, what it does is to shift the Laplace variable. The Laplace variable here is s. So it shifts the Laplace variable by a certain constant v. So the shifting property shifts the Laplace variable, or the complex variable, which is s. Shift the Laplace variable s by a constant, by a certain constant, right? So this is what the shifting property does. So if we can recall the definition of the Laplace transform, if we have the Laplace transform of a function f of t, this is equal to the integral from 0 to infinity of e to the negative st f of t dt. So this one is the same as capital F of s, and this is equal to the integral from 0 to infinity of e to the negative st and then f of t dt. Cool. Now the shifting property, we are going to shift this Laplace variable s by a certain constant. So let's call that constant b. Why not? So we are going to apply the shifting property here. So s minus, we are going to shift it by a certain constant b. You can have s plus b if you want, but let's stick with negative for illustration purposes. So this is equal to the integral from 0 to infinity of e to the negative. You are now going to replace s here with s minus b. That is equal to s minus b multiplied by t and then f of t dt. Cool. So f of s minus b, this is equal to the integral from 0 to infinity. Applying laws of indices here, this is e to the negative st. This is multiplied by e to the positive bt and then f of t dt. Cool. So this one, applying the definition of Laplace transforms, if this one is the Laplace transform of the function f of t, what is this one? That is the Laplace transform of the function e to the bt multiplied by f of t. So the shifted function, that is shifting this Laplace variable by b, we are going to have this. This one is now equal to the Laplace transform of the function e to the bt and then f of t, like this. So this one is the Laplace function of the function e to the bt multiplied by f of t, right? Okay, so how can we use this one to solve these functions? We want to find the Laplace transform of all these functions. So we are going to apply the shifting property to be able to find the Laplace transforms of all these. Alright, so the first one, let me switch colors and then we look at the first one. So the first one is the Laplace transform of e to the bt. This is multiplied by sine of at, right? So this is equal to what? So from what we have, we will have to find the Laplace transform. We will have to find the Laplace transform of the function. The function here is the sine of at. So we find the Laplace transform of the sine of at, and then we are going to shift the variable s by b. So that is what we are going to do here. So what I have to do here is to pretend as if this one doesn't exist, and then you are finding the Laplace transform of sine of at. So the Laplace transform of the sine of at is equal to a divided by s squared plus a squared. But we will have to shift the variable s, that is the Laplace variable s, by s minus b. That is what we have here. So here we are going to shift the variable s. So we are going to put s to be equal to s minus b. And this is equal to a divided by s minus b all squared plus a squared. And this one is the Laplace transform of this function e to the bt multiplied by sine of at. Yeah, so that's the first one. So now let's go up and fill it. So this one is going to be a divided by a squared, s minus b all squared plus a squared. Cool. The second one is the cosine of at multiplied by e to the bt. Okay, cool. So 2 the Laplace transform of e to the bt, this is multiplied by the cosine of at. So this is equal to, we are going to pretend as if this one doesn't exist, and then we find the Laplace transform of the cosine of at. And Laplace transform of cosine of at is equal to s divided by s squared plus a squared. Cool. So we are now going to shift our Laplace variable by b. So this means we are going to substitute s with s minus b. So this one is equal to, we have s minus b all over s minus b all squared plus a squared. And this one is the Laplace transform of the function e to the bt multiplied by cosine of at. So now let's go up and then fill our table. So this one is s minus b divided by s minus b all squared plus a squared. Cool. Now the next one is e to the bt multiplied by sine hyperbolic of at. Cool. So now the third one is the Laplace transform of e to the bt. This is multiplied by sine hyperbolic of at. This is equal to, pretend as if this one doesn't exist, and then we find the Laplace transform of the sine hyperbolic of at, which is a divided by s squared minus a squared. Then we are going to put s to be equal to s minus b. So this one is equal to, we have a all over s minus b all squared minus a squared. And this one is the Laplace transform of e to the bt multiplied by the sine hyperbolic of at. So here we have a divided by s minus b all squared minus a squared. Cool. Now the next one is going to be the cosine hyperbolic of at multiplied by e to the bt. The Laplace transform of e to the bt multiplied by cosine hyperbolic of at, like this. Pretend as if this one doesn't exist. That's the drill. And now we are going to have the Laplace transform of the cosine of at, which is cosine hyperbolic of at, which is s divided by s squared minus a squared. This is what we have, but we are going to substitute s with s minus b. That is the shifted s. So this is going to be s minus b divided by s minus b all squared minus a squared. And this one is the Laplace transform of e to the bt multiplied by the cosine hyperbolic of at. So s minus b, this is divided by s minus b all squared minus a squared. And the last one is e to the bt multiplied by the polynomial of the nth power. That's the last one. So the last one I will do in blue. So the last one is the Laplace transform of e to the bt. This is multiplied by the polynomial to the nth power. This one is equal to, we are going to pretend as if this one doesn't exist, and now we'll find the Laplace transform of t to the power n. And if we can recall, that is from our first video, this is the n factorial divided by s to the power n plus 1. So we are going to substitute s with the shifted version, which is s minus b, and this one is equal to n factorial divided by s is now s minus b, and this is raised to the power n plus 1. So n factorial divided by s minus b all to the power n minus n plus 1 is the Laplace transform of this function. So we are going to complete our table and now work few examples. So this one is n factorial divided by s minus b. This is raised to the power n plus 1. So our table now is complete. So what I'm going to do is to go ahead and now work few examples and see how this is done. Okay, so now let's work few examples. So we are going to have some examples here. So let's say the first one, we are asked to find the Laplace transform of e to the 2t. This is multiplied by the sine of 3t, like this. Cool. And now next one, we are going to find the Laplace transform of e to the negative t, and this is multiplied by the cosine of 4t. Cosine of 4t, like this. And now we are going to find the Laplace transform of e to the 2t, and this is multiplied by the cosine hyperbolic of 3t, like this. So just for the purpose of illustration. So now let's work them. For the first one actually corresponds to what we have here. So the first one is what we have here. That is a divided by s minus b all squared plus a squared. All right. So the first one here, so the Laplace transform of e to the 2t multiplied by sine of 3t, this is equal to, this is we have to find what a is. So a here is equal to 3, b is equal to the constant in the exponential function, and now we can now apply the formula. So the Laplace transform, which is now f of s, this is equal to a here is 3 divided by s minus b, so s minus 2 all squared plus a squared, and this is equal to 3 divided by s minus 2 all squared plus 3 squared is 9, like this. The second one is e to the negative t multiplied by the cosine of 4t. That is the Laplace transform of e to the negative t. This is multiplied by the cosine of 4t, like this. So here we have to find a here is equal to 4, and b is the constant in the exponential function. So the constant here is equal to -1. All right, so b is equal to -1. So now f of s is equal to, we have to use the second one, that is this one, that is s minus b all over s minus b all squared plus a squared. So s minus b, so s minus b, but b is -1, divided by s minus b, b is -1, all this one is squared, and then plus a squared, a is 4 squared. So this is equal to s plus 1 divided by s plus 1 all squared plus 4 squared is 16. This is the second one. And then the last one is e to the 2t multiplied by the cosine hyperbolic of 3t. So the Laplace transform of e to the 2t multiplied by cosine hyperbolic of 3t, like this. And we have to find a and b here. A is equal to 3 and b is equal to 2. Cool. So now we are going to use this one, that is s minus b divided by s minus b all squared minus a squared. So the Laplace transform of this function is equals to s minus b. So we have s minus 2 divided by s minus b, b is 2 all squared minus 3 squared. And this is equals to s minus 2 divided by s minus 2 all squared minus 9. Alright, so these are the Laplace transforms of these functions. So that is the shifting property of the Laplace transforms. It allows us to calculate the Laplace transforms of an exponential function multiplied by a function f of t. So in my next videos, I am going to continue finding the Laplace transforms of of t raised to the power n multiplied by a function f of t. So if a polynomial is multiplied by a function f of t, how do we take the integral, the Laplace transform of that function? So if you enjoyed this video, you give me a thumbs up and subscribe to Calculus Diaries, and you join me in my next video as we calculate the Laplace transform of a polynomial multiplied by a function f of t. I will see you in the next one. Bye bye.